Way.
Okay, thank you very much. Okay, perhaps you should save the clapping for after the talk. You may not like it. So, anyway, so today, thank you so much for having me here. Today, I will try to give you a taste of the questions that we're trying to address in particle physics these days and how we are trying to address these questions. In my effort to do this, I would also like to invite you to ask questions during the talk. I know it's a big room and it's a bit intimidating, but please do. It makes everyone feel more comfortable. Particle physics is the field of physics that tries to understand and reduce what you see around us, in the least amount of equations and the least amount of ingredients. It follows a very old idea put forth in the 13th century by William of Ockham. So we've been doing this for quite some time, for centuries in fact. And we have been quite good at it. Based on this idea of having our theories be as simple as possible, we have managed to establish what is known now as the standard model of particle physics. It's a theory that has about 20 particles and 20 parameters. And it's able to describe a wide range of phenomena. You may have seen this picture before. So you see here, around in the circle, you see all the particle content of the standard model. The outer circle is the matter fields, what we are built out of. The inner circle is the force carriers, the gauge bosons, the particles that mediate the three forces that we know of in the standard model: the magnetic force, the weak force that is responsible for radioactivity, and the strong force that holds nuclei together. And in the center, there's the latest component that was discovered at the LHC, the Large Hadron Collider, the Higgs. So, as you can see, it's quite compact. And as I said, it has been very successful. With this amount of ingredients plus gravity, Einstein's equations, we've managed to successfully describe phenomena that we observe in a wide range of scales. We can describe phenomena that we see in scales of the galaxy all the way down to subatomic scales. In fact, there are aspects of the theory that we have tested to a precision of 1 part in 10 to the 13. What does that mean? It means that we've made a theoretical calculation to a 13 decimal precision, which means you have a decimal point, you have about 12 digits and 13 digits after the decimal point. So someone actually computed a quantity to that level. And we managed to measure the same quantity with experiment to the same precision. Okay? So the quantity that I'm referring to is the G minus what is known as the G of the electron. It's the gyromagnetic ratio of the electron, which compares the magnetic moment of the electron to the Bohr magneton. Okay? So imagine you have a theory where experiment and computation agree to such degree. Now, another core idea closely related to the idea of minimalism that has brought about this enormous success is the idea of unification. The unification of phenomena. And again, this goes back centuries. It started with Newton. Newton was the first person. Newton, first of all, was the most amazing physics genius that has been around in millennia. So he is someone that has managed he realized that terrestrial phenomena, the way things fall on the surface of the Earth, and celestial phenomena, the way planets move around each other, around the sun, actually are described with a single theory, the theory of gravity. Now, later on, the latest success, the next step in unification came with Maxwell. Maxwell realized that what till till that time, people were describing with different sets of equations, affects electricity, light, and magnetism. He unified in one single theory by writing down his very compact equations, the theory of electromagnetism. Today, the Standard Model unifies the success it does, the unification success it has, is the success of unifying the theory of electromagnetism, Maxwell's theory, to the weak force. The force that is responsible for radioactivity, and it's mediated by the W and the Z boson, to a single theory, to a single force, the electroweak force. So, okay, I've advertised it very well. So the question is, since we have such great success, why do we need to move beyond the Standard Model? Why is there a need to move beyond the Standard Model? And the reason is, one of the main reasons is, well, we've managed to calculate quantities at the 13th decimal precision, but those quantities describe involve only 5% of the energy budget of the universe, the matter sector. 95% of the energy budget of the universe is made up of components that we've only seen through the force of gravity. There is dark matter, which is 5 times the amount of matter we have. We call it again matter because we see it behaves under gravity, same way the Earth behaves, the Moon behaves, we behave under gravity. But it doesn't interact with light, so we call it dark. Now, there is even a bigger component. Actually, the dominant component of the energy budget of the universe is an even more mysterious one. It's called dark energy. Or in particle physics circles, we call it the cosmological constant. What is that? So it's a very weird form of energy density. So imagine you take a balloon, okay, and you inflate the balloon. So as you make the balloon bigger and bigger and you're holding it in your hands, you feel the air inside getting colder. And the reason is that as the air inside expands, the molecules, the temperature inside of the air inside the balloon, has to diminish in order to keep the same total energy inside the balloon. Okay, so the molecules start getting colder. Now imagine that you had some energy density that as you make in your balloon, which is the universe, bigger, as the universe was expanding, that energy density was not diluting. It was always there. This is exactly what the cosmological constant does. And given its sign, it can make actually things expand or collapse. For our universe, it seems like it's making things move away from each other. And in fact, because we are dominated by dark energy, it predicts a very grim future for our universe, okay? We lose sight of nearby clusters of galaxies, and it will be a very cold, dark place, but we don't have to worry about it. We'll all be gone till then. So the next, another open question is what is known as the flavor problem. So if you look at all those matter fields that I showed before, they are divided into 3 families. 3 families of particles that interact. Each family interacts the same way under the gauge forces, under the forces, but it has different masses. In fact, the Standard Model particles are spread over 6 orders of magnitude in energy, in mass. And the question is why? Why are they not all the same mass? Why aren't all particles, why isn't the electron as heavy as the Higgs particle, as the top quark? This is something that we don't understand. There are theories about it, where this hierarchy could be coming from, but we don't have a definite answer yet. There is also the problem of matter-antimatter asymmetry. The way we understand the Standard Model now, it predicts that there shouldn't be a leftover component of matter that we observe today. We wouldn't be here. The universe would have been created with almost equal amounts of matter and antimatter that would have annihilated away long before we would come about. So the fact that there is matter that we are here today is a big puzzle. Now, and to go back to the theme of unification, one bigger picture question is, now that we understood that electromagnetism and the weak force are united under a single force, how do you combine all the rest of the forces? There is a nuclear force that binds the nuclei, and there is also gravity. So what is the grand unified theory that brings all these together, all the forces together? And there is a basic challenge to this, and it's the weakness of gravity. So this is something that we normally don't think about because we are bound to the Earth. Sometimes it's hard to jump, it's hard to go upstairs. But every time you lift something, every time you with your hand, you lift up a glass of water, the electromagnetic forces in your hand overcome the pull of the entire planet on this glass. So if you were to put it in numbers, so for example in the hydrogen atom, where a proton is, when an electron is bound around the proton, if you calculate the gravitational force and compare it to the electromagnetic force, you find a number that's extremely small. You find, if you count them, there should be about 39 zeros here. Okay? So gravity is extremely weak. So how do you unify a force with all the rest of that's so much weaker than every other force that we know of in nature? How do you bring all these things together? This is also known actually as you may have heard it as the hierarchy problem. Okay, it goes by another name. An equivalent question is, why is the Higgs particle mass so much lighter than the Planck mass? So I will take, starting from motivated by the hierarchy problem, I'll tell you an approach that tries to address the hierarchy problem or the extreme weakness of gravity, the theory of large extra dimensions. And then from there, I'll talk a bit about the LHC. Naturally from there, from the theory of large extra dimensions, I will tell you how it motivates a new type of worldview that suggests that the universe is not unique, that there is a multiverse. And I will discuss it in the context of string theory. And then from that, I will explain to you how that same picture also gives rise to new particles that lead to new experimental directions, completely different and complementary to the LHC. So the theory of extra dimensions is something that was put forth about now it's more than 20 years. So in these theories, imagine that there are three spatial dimensions, like a sheet of paper. Okay? So we are confined, all we experience is the photons, the strong force, the weak force, is all confined to live on the sheet of paper. The matter fields, everything. Now, perpendicular to this, there is an extra dimension, an extra spatial dimension. Gravity, because it's closely related to geometry, sees all of the dimensions. And because it sees all of the dimensions, all the extra space, its strength gets diluted. So it's like if you have a very strong river, and if the river is broken apart in little streams, and you sit by the stream, you never see the full strength of the flow of the river. But if the streams all come together, you see that the flow of the river is very strong. So because we experience the geometry only from a three-dimensional point of view, or from our point of view, we see the effect of gravity on us, but we don't see the full effect of gravity in the entire geometry. I should say that these extra dimensions have to be really, really small. They're not infinite in size. Otherwise, Newton's law wouldn't work the same way it does. A very nice analogy, actually, because this is a theory that my advisor, Stavros Dimopoulos, put forth. And a nice analogy is a billiard table. So you can, if you're good at billiards, the balls will be confined on the surface of the table. So you can imagine this as the colliding particles. But the sound waves that are produced during the colliding billiards, you can think of as the gravitational waves, and those are, there's no way you can confine them to the surface of the table. And the way to look for these things is at colliders, okay? Because it's related to the Higgs mass, and you expect these effects of the extra dimensions to manifest themselves, and I will explain how at colliders. You've probably seen, if you're physics enthusiasts, you've seen pictures like this before. This is the LHC tunnel, and this is the picture of the CMS detector, the prettiest one of the two. Atlas is the biggest one, but this has better colors. They're both amazing experiments. So, fun facts, of course, about the LHC is it shows you, for me, it's a proud moment in humanity because it tells you what great things we can do when we all come together for a common cause. So it's an international collaboration of thousands of scientists around the world. You have in these experiments proton beams that have the width of the human hair going around in a 27 kilometers circumference. They pack each one of the human hair size beams carries the energy of a TGV train, a very fast French train. They collide at the interaction points. They get diverted at certain points where the detectors are, or the CMS experiment or the Atlas experiments are. And you produce tons of data there. So you get billions of collisions per second, and the amount of data you have is enormous. In this amount of data, we believe there could be evidence of this existence of theories of large extra dimensions. So what happens in these theories? So as you collide the two proton beams at the LHC, you expect, just like the sound waves on the billiards table, you expect gravitons to escape in the extra dimension. So if you were to sum up the energies of all the particles that are produced during the collision, you would find a deficit. So we'll find what is called the missing energy component. Another thing that would happen, because as you have access to these extra dimensions, you start seeing that gravity is actually strong. So what will happen at the LHC? You'll start producing actual black holes. You'll start seeing black holes and the effects of quantum gravity. So these small black holes that are formed at the LHC will evaporate very quickly and be a little explosion in your detector. So, of course, this has been, you may have heard there was a famous lawsuit that said that the LHC will produce a black hole that will eat up the Earth. But luckily for us, this won't happen. This is highly impossible. And the reason is that there is a cosmic collider that we know of already. So we bombarded constantly by cosmic rays. These cosmic rays can pack energy that is much higher than the LHC. So when they collide with molecules in the atmosphere, they can create black holes. So if this were to happen, we wouldn't be having this discussion, this argument right now. Large extra dimensions can thus give us a very, very interesting and unique signatures at the LHC. At the same time, they provide us with an interesting worldview, new worldview. So I said now that imagine that our world is like a sheet of paper in these extra dimensions. So what if there are other sheets of paper? What if there is an entire book? So it could be possible that in these extra dimensions, you have other universes that you don't have access to, because They are confined to live in their three-dimensional or two-dimensional space, and we are confined to live in our space. So we are led to the following possibility. So far, we've been considering theories where we are unique. There's just what you see around you. There's just this one universe. But what happens if there are more? So this actually, also it's very philosophically different from the idea of what Occam proposed. So Occam suggested that, of course, we should be, if you take Occam literally, there should be only one universe, but we are brought forth with the possibility that there is many. And this is something actually that Leibniz in the 17th century strongly advocated for. He said that nature can only be perfect if all possibilities are realized. And in fact, you can see there is a very stark difference in their styles and lifestyles. So, as I said, minimalism has been very successful, and it's been leading us, but it's not the first time we are faced with such a dilemma. Centuries ago, millennia ago, people thought that there was only one solar system. In fact, people even put the Earth at the center of the solar system. So at that time, people were trying to explain what is the size of the planetary orbits, why are they the size that they are. But with the discovery of the telescope, we discovered that our solar system, in fact, is not unique, it's not even special. There is about 10 to the 22 solar systems in the universe. Of course, things like that we take for granted today, but back then it was a huge thing to say. It was a very brave thing to say. So Giordano Bruno, the first person to postulate that stars that you observe in the sky are like solar system, was burned at the stake. So what does that important discovery that today, what does that discovery that we take for granted today, how did it change the way we think about physics? First of all, it changes the way that we think about our solar system. It changes what type of questions we have to think about dynamically. Before, if you only had one solar system, you had to understand why the Earth-Sun distance is one astronomical unit. Why does it take 8 minutes for the light from the sun to reach us? If you have 10 to the 22 solar systems, the Earth-Sun distance, the distance between a planet and its star, becomes a matter of historical coincidence, just a statistical thing. The other question is, if you have one solar system, then it becomes, versus many, it begs the question, why does Earth host life? If you have many, then it becomes an issue of environmental selection. If you have many, we just we see that Earth is in the right distance from the sun, so that it's not too close that we get burned, or too far that we are too cold. It has an atmosphere. So it points to what we call environmental reasoning. Actually, people that look for exoplanets, they look the zone that the planet can be in the right temperature. They call it the Goldilocks zone. So now, as I said, we are brought with a similar dilemma. So is there one universe, or are there many? And I talked about how this can actually arise in theories of extra dimensions, and such a theory is string theory. String theory is, in fact, another attempt at unification. It's a theory that tried to unify quantum mechanics and gravity. Okay? And in order to do so, it needed extra dimensions. It needed extra dimensions to be mathematically consistent. So the way you think about this extra dimension string theory, so you can imagine that our world is again this sheet of paper. We're confined to live here. The extra dimensions are perpendicular to this, and you can think of, they can be more than one. In fact, in most versions of string theory, there's 6. And these have to be compactified. They have to be made small for Newton's law to work as we see it. So you can think about them being compactified simply on a sphere, and every point in this universe, you can think of this little sphere sitting on top. They can be compactified in a donut shape, and in fact, you can increase the complexity of the compactification. This is what is called, this is a plot, a picture attempt at the 6-dimensional Calabi-Yau manifold. So basically, the complexity of the geometry is only limited by the of our imagination, the theorist's imagination. So there are many possibilities about how these extra dimensions in string theory are made small, are compactified. Now, each different compactification results in different particles, in different forces, in the dimensions that we can see, that we live in. Okay? So each one, compactification corresponds to a different theory. And as a result, it corresponds, we can say it corresponds to a different vacuum, or if you want, a different universe. This universe will be vastly different from each other. These theories are completely different from each other. So, so the laws of nature depend on the shape of these extra dimensions. So it looks like string theory, even though it started from the idea of unification, trying to unify gravity and quantum mechanics, it may be pointing to an idea of plenitude, naturally. Okay? So what does that mean? How does this universe even look like? In fact, we believe that most of the universes are completely empty. And the reason is the following. So in most of these universes, the dark energy component is so big that it breaks galaxies apart. Okay? So I told you about early on about the dark energy that we measure in our universe, and in fact, it's a huge mystery. If you were to calculate in our theory, in the standard model, what the dark energy component is, or the cosmological energy, a cosmological constant is, you would find the value that is at least 60 orders of magnitude larger than what we measure. 60 orders of magnitude. What does it mean? It means that in the standard model predicts that the universe should be this big at most. Literally a few millimeters in size. Okay? So a big puzzle is, why is the universe so large? Why are there even galaxies? You cannot fit a galaxy in here, right? So why are there even galaxies? So this is what is known as the cosmological constant problem. And in fact, in most of these universes that are predicted in string theory, this is exactly what happens. Most of them are tiny. They have such a huge value of the dark energy component, of the cosmological constant component, that they won't allow for galaxies to grow. So they're completely empty. Okay? But once in a while, if you have many, accidentally, you will find one where the dark energy component is accidentally small. Kind of like the Earth-Sun distance. It's an accident. And this is where we would be. So now if we were to stick with the idea of a single universe, we would have to find, and people have tried, we would have to find a dynamical explanation why the universe is large. Why isn't the universe a few millimeters in size? And we have tried, and we have found no theories that explain this. No dynamical, no symmetries, nothing. no new physics that can explain this. So we'd require some sort of miracle to explain the single universe idea why this happens. So in the case of string theory, it gives you a natural framework where these can naturally arise. It becomes a matter of historical coincidence. If you have many of these universes, different one will have different values of the dark energy component or the cosmological constant component. But once in a while, there would be one where by accident, this value will be small. And this is where we can be. This is what is known as the anthropic principle or environmental selection. And of course, and now you can ask me, okay, but isn't this philosophy? How do we look for these things? These are things that we cannot see the light from. These are universes that are outside our causal horizon. So what is the analog of the telescope that led our ancestors to realize that they shouldn't be thinking about the single solar system? And luckily for us, there could be, even though we cannot observe these universes directly, there could be indirect probes that tell us about their existence. Okay? And of course, because it's indirect, it will take a lot of experimental effort, and it will take a lot of measurements to clarify such a picture. But there is still a chance. In particular, where you have a framework such as string theory, you can try to make predictions. So first of all, one positive evidence for the existence of such a structure, it's, as I explained, the fact that there is a way in this string landscape to understand how we solve the dark energy problem, the cosmological constant problem. People have proposed there is other theory. There is even LHC signatures. There are theories called split supersymmetry that can give signatures at the Large Hadron Collider that are motivated by the string landscape. And what is more relevant for the rest of my talk is that the same complexity that gives rise to this plenitude of universes, this complexity in the extra dimensions, can also give rise to a plenitude of particles, to many particles that we can exist in our universe, and we can detect with experiments we can do in the lab or astrophysical observation. These particles go by funny names. They're called axions, moduli, dilaton, dark photons. You don't have to remember these names. For physicists, when you call a particle a name, it tells you something about the way it's behaving, its properties, and the way it couples to us. So they have, all these particles have different properties, but they also have many things in common because they arise from this picture of complexity in string theory. So first of all, these particles interact very weakly with us. In fact, in many cases, much, much weaker than gravity. So they cannot be produced at colliders. You cannot collide protons and produce these particles. These particles can be very light. In fact, they can be lighter than a billionth of the proton mass. They can be the dark matter. They are natural candidates to explain the dark matter component of the universe. They can also mediate weird new forces that are different from gravity. In fact, they can be much, much weaker than gravity. And given that they're much weaker than gravity, you have to design very precise experiments so that you can isolate their effect from the ordinary environment that we live in. And this is what goes by the experiments in this regime go by the name of the precision frontier. Okay? So most of these are, of course, there are big experiments here. The LIGO experiment that recently discovered, a couple of years ago, discovered gravitational waves for the first time. This is an example of a huge precision experiment. But most of the time, they're tiny. Most of the time, these experiments can fit on the table of an experimentalist laboratory. And they can be different things. So you can use, and I will describe how this works. You can use techniques that are where the MRI machine is based to detect dark matter. You can use the clocks, atomic clocks, which are the most precise clocks that we know of, to detect new forces in dark matter as well. You can use them to detect gravitational waves. Many of these things, these ideas of these experiments, precision experiments, trying to look for a tiny, tiny effect on an experimental setup is very old. What is new is that while particle physicists, many particle physicists were focusing on the collider effort, in other fields of physics, people were understanding and expanding, things and expanding their techniques. And now what we are doing in the last few years, we're bringing in this knowledge acquired in other fields of physics and try to apply it in ways that we can learn, to apply it and see what we can learn about beyond the standard model, about dark matter and new forces, any type of new phenomena. So now, before I describe you some examples of what these precision experiments can be and what these precision probes can be, I have to do a parenthesis and explain to you something about these particles, and in particular their size. Okay? So usually, the bottom line is that lighter elementary particles are bigger in size. And this is very counterintuitive because for all of us, more massive things are also bigger, right? Like the Earth, we become more massive, we're bigger. But for elementary particles, this is not the case. It goes the other way. So the way to understand this first is to keep in mind that there is a direct connection from E equals mc squared between mass and energy. Okay? So now we'll start talking about energy. So here you see two pictures of a cat. These pictures were taken observing photons of different energy. On the left, you have a picture of a cat with thermal imaging, with photons that are emitted from its own heat, of temperature about 20 degrees centigrade, or in Fahrenheit, it's about 70 Fahrenheit. Cannot do the conversion very well. So now the picture on the right is taken by optical photons. Optical photons are the photons that are emitted from the sun, and those have a characteristic temperature of 3000 Kelvin, 3000 Celsius. So they're much, much hotter. So that means they're much more energetic. So you see that with less energetic photons, you don't have as good resolution as with more energetic photons. So more energetic photons have better resolution. They probe shorter distances. They correspond to shorter wavelengths. That is smaller size. Okay? So this is a very quick way to understand why, for example, when people sometimes talk about the LHC, they talk about how you can probe the universe at very short distances. And this is exactly the same idea. As you collide the protons at higher and higher energies, you probe shorter and shorter distances for elementary particles. And again, this clearly shows us that you do have some idea, if you think about it, about elementary particles. You have some idea of their size. Now, these ultralight particles that I talked about before, these particles that arise in this string landscape, are very, very, very light, so they have to be huge. In fact, they can be as big as the universe. But you still know examples of huge particles. For example, take radio waves. Radio waves are photons. The AM frequency corresponds to wavelength of 300 meters. So every time you're tuning your radio to AM, I mean, of course, most is FM, so that's about a factor of 10 shorter wavelength. You tune your radio to look at the effects of 300-meter-sized particles. Okay? The gravitational waves that advance LIGO So the gravitational waves that advance LIGO saw are gravitons, the force carrier of gravity, and they are bigger, they have a size that's bigger than the size of the Earth. Okay? In some cases. So they're about the size of the Earth in some cases. Now these ultralight particles brings us to the possibility that dark matter itself can be thought of as this giant particles, accumulation of particles that's stuck in the galaxy. So how do you look for these? How do you look? Keep in mind, I want to look for very, very big things, very, very big particles. And the way you can do it, one way you can do this, is by observing black holes. Okay? Black holes, astrophysical black holes, have a characteristic size, which is the horizon size, the distance from which nothing can escape the black hole's gravity. So it turns out there is an effect in general relativity called superradiance, under the influence of which astrophysical black holes become the probes of particles that have a similar size. And this is very exciting because now we've seen black holes. 2 years ago, it was the first time we saw a black hole merger in the sky. So we know now without a doubt these objects exist in our universe. And in fact, with our next run of the LIGO experiment, we expect to see at least 50 more of these. So what was initially a sensation now becomes a tool that we can use to discover new things, to understand new things. So how do black holes probe new particles? As I said, there's an effect called superradiance that allows black holes to become probes, particle discoverers. So the way this works is the following. First of all, this effect of superradiance has nothing to do with GR. It's an effect that can be observed in a wide variety of systems. Okay? Basically, all you need is the system to have some friction, some dissipation embedded in it. So now let's imagine the following thought experiment. So take a cylinder that has a rough surface, okay, and start spinning the cylinder. Now take a little ball or a particle, or a little ball, and scatter the ball tangentially from the surface of the cylinder as the cylinder is spinning. If the ball and the cylinder at the point of contact, if the ball is moving more slowly, if the cylinder is moving more slowly than the ball at the point of contact, they will move like this. They will graze, and the ball will slow down. So the ball will come out with lower kinetic energy than what it came in with. So friction would have taken energy from your ball. Now speed up the cylinder even more. At some point, when the cylinder starts moving faster than the ball, because of friction, it will grab onto the ball and give it a push. So if you have a cylinder, in this case, the cylinder, due to friction, it will actually be giving energy to your system, not taking energy away from it. Okay? So you will see something like this. A similar thing, I was talking about a ball, similar thing can happen for a wave. Okay? So you take a wave and you scatter it from a dissipative cylinder. What can this dissipative cylinder be? For example, for an electromagnetic wave, for a photon, this is a conducting cylinder, a cylinder that has some resistance. Okay? That's dissipation for the motion of electromagnetic waves, resistivity. Now, if the cylinder is rotating faster than the angular velocity of the wave, of the electromagnetic wave, the wave will come out with higher amplitude than what it came in with. So the wave during the scattering process will be amplified. So you gain energy from the process. You extract energy from the cylinder. You don't lose energy. Your wave during the scattering process does not lose energy. So how can something like this happen for black holes? So black holes, astrophysical black holes, we believe that they are rotating. Okay? Check mark number 1. The other thing that they have, in fact, they have a region around them called the ergo region, where even light has to rotate. This is the region that signals to the world, through curving, changing gravity around it, that the black hole is rotating. Now, the other thing that they have a horizon. A horizon, in fact, is a perfect dissipative system, the perfect absorber. Anything that you throw in the horizon gets absorbed. So, if you take a wave, for example, this can be electromagnetic wave, this can be a gravitational wave, and you scatter it from the black hole, you can find if the angular velocity of the black hole is faster than the angular velocity of the wave, you can find that the wave can come out more amplified than it came in, okay? With higher amplitude than what it came in with. And this is something that people have known about gravity since the 60s. In fact, in 1972, President Tucholsky did this cute thought experiment where they said, okay, let me scatter my wave from the black hole, the electromagnetic wave, while at the same time surrounding the black hole with a perfectly spherical mirror. So what will happen as the wave gets reflected back and forth from the black hole, continuously getting amplified, this amplification becomes exponential, and the radiation portion becomes so large that the mirror eventually explodes due to the radiation pressure. And they call it the black hole bomb. Okay? During this process, the black hole spins down. Now, okay, this is fun and games, it makes a nice cartoon, so why does this have to do with real physics? We cannot go around the black hole and build perfectly spherical mirrors to do these experiments. So there is something though, so I talked about photons and gravitons. Photons and gravitons are special because they have no mass. Their mass is absolutely zero. So they cannot have bound orbits around the black hole. So you can only scatter them once from the black hole. Imagine now that your wave that you scattered from the black hole had a mass. So it was the wave of a massive particle. Then the particle creates a bound state from the black hole. So the mass of the particle acts like a mirror that confines it to the vicinity of the black hole. And what you get is the following. You get a gravitational atom in the sky. So what happens is now you have a black hole that's spinning. You can think of this as the nucleus of your gravitational atom. If you have a particle, this process is most efficient when the size of the particle, which is related to its inverse mass, is comparable to the black hole size. What you will see happen is the following. You will see the black hole spinning down and a cloud of particles being created around the black hole. I call it a gravitational atom because this is exactly what it looks like. If you solve for the energy levels of these bound states, you find a similar formula that you do for the hydrogen atom. There are several differences, of course. First of all, the size. A hydrogen atom, because it's bound by electromagnetism, and the mass of the electron is so much heavier, the size of an atom is about an angstrom, 10 to the minus 10 meters. This is about at least a trillion times bigger. Okay? The shape of these bound orbits is exactly as picture of atomic orbitals, if you have seen those. And they're described with similar quantum numbers. Okay? Now, another very important difference is the type of particle that you can have occupying these bound orbits. For a hydrogen atom, the particles that occupy these bound orbits are electrons, fermions, so you can only have 2 per bound orbit. For these particles that I'm talking about, coming from the string landscape, you can have their bosons, so you can have more than 10 to the 77. It doesn't mean much to you, but you can translate it. So if you were to count how many protons there are in every star in the universe, you would have more particles than protons around the black hole. Okay? So we're talking about huge number of particles going around the black hole. Now, because they have this huge number of particles, the black hole can start emitting particles. It starts behaving exactly like a laser. And it starts emitting gravitational waves and particle waves. Both of these you can detect with gravitational waves in particular, you can detect with experiments such as advanced LIGO. So basically, this is a process that turns the astrophysical black holes that could be roaming around in the galaxy, turns them to gravitational wave beacons. And you can look for these signatures coming from those. And this is just the force of gravity, by the way. This doesn't make any assumptions about the couplings these particles can have with us, and it doesn't make any assumptions about the cosmological evolution of these particles. So, as I said, though, these particles could explain a significant missing component of the energy budget of the universe. So they could be the dark matter. So usually, if you think about, if you were to picture the dark matter, you usually think about little particles moving around like a gas. But if these particles are very light, a more accurate picture of the dark matter trapped in the galaxy is like a wave. It's like a radio noise. This dark matter radio noise has a characteristic frequency that's set by the dark matter mass. And actually, you can design experiments that can tune into that particular frequency, and you can try to detect this oscillation. An important fact is, the reason we can do this is because these types of dark matter particles interact with us so weakly, they permeate everything. Everything that you see around you is immersed in this dark matter noise oscillation. And if they couple to us in non-trivial ways, they can communicate this oscillation to our device. How depends on the type of particle you have. For example, I mentioned briefly the word modulus. So if the dark matter is a modulus, it will have very specific properties. Moduli in string theory are fields, particles, that determine the value of fundamental constants that we measure. For example, they determine the value of the electron charge or the electron mass. So if such a modulus, if the electron charge modulus is the dark matter of the universe, it's trapped inside the galaxy and it's oscillating, the oscillation of the dark matter will be communicated to the fundamental constant it determines. So it will be communicated to the electron charge. So what you would see if the dark matter is this type, you would see locally the electron charge oscillate. Okay? Yes? Good. That's an excellent question. I wish we knew. So this is where also the setup of tabletop experiments come in. You have to cast a wide web. String theory does predict the existence of these very light particles, but we have no way of calculating precisely where that range should be. So you have to build different experiments to cover different parameters, parts of the parameter space. And this is where the idea also of tabletop experiments. You cannot build a $1 billion machine to probe one little part of your parameter space. So depending on the frequency, you can design different experiments. So for example, you can build atomic clocks. Atomic clocks, the ticking rate of atomic clocks is set by the energy splitting of an atomic level. And that depends that the value of the energy splitting is determined by the value of fundamental constants. So if the electron charge is oscillating, it means that the ticking rate of an atomic clock will be oscillating. And that we can measure very precisely. For example, for an atomic clock, so I think a wristwatch has, if you were to translate its frequency stability, you will get something that it loses 1 second every year, which is pretty good. An atomic clock loses 1 second every 15 billion years, which is more than the age of the universe. And they are making even more stable atomic clocks now. Okay? So any tiny effect, when you expect the effect of the dark matter to be tiny, will modulate that ticking rate. So you can design experiments that look for this effect of the oscillation. In fact, we've made a lot of progress, and I mean, it doesn't make sense to show such plots here. We've made a lot of progress by just reanalyzing existing data of atomic clocks. They're already sensitive to this type of dark matter candidates, just by data that's lying around. The other thing you can do to look for this type of dark matter is with tuning rods, essentially, with resonant mass detectors. How does that work? So if the electron charge is oscillating locally, it means that the Bohr radius of atoms is changing. So the atom size is changing. Of course, the change in a single atom size is unmeasurable, but luckily for us, solids put atoms next to each other. So what happens in this case, an entire solid is breathing with the dark matter. If the frequency of the dark matter matches the vibrational resonance of the object, then it can excite it. So this is another way you can look for it. And in fact, people have had this idea to look for gravitational waves. So Joe Weber, back in '69, he took a big piece of metal and he tried to look for the tidal force of a gravitational wave coming by. If the frequency of the gravitational wave matched the vibrational resonance of the rod, it would be excited and he could measure it. In fact, he thought he found something, but no one was able to reproduce his results. So this technology has evolved a lot today. So you can use similar setups to look for dark matter. In fact, a fun fact is that the Earth itself it's a type of tuning rod. So during one of these big earthquakes, back I think it was the 60s, people measured that there was a breathing mode of the Earth with a period of about 20 minutes. And it got excited during one of these big earthquakes, and it died off over a period. The seismographs around the world measure decay over a period of months. So you can use this mode. This mode can be excited with dark matter. So if you were to translate it to a bound in dark matter searches, you would find that the Earth does better than any experiment we have done in the lab, in a very narrow resonance. Of course, you cannot use it at discovery because an astrophysical object you don't have any control over, such as Earth. So, but it's really cool. So this brings us to the end of my talk. I mean, I could tell you all sorts of examples of experiments and signatures of new physics. And the bottom line is that we find particle physics finds itself in a crossroads. For many years, we've been following the idea of minimalism, the idea that we should make our theories as simple as possible. But now we are given another option. We are faced with a puzzle and a possibility that this is not right. That in fact there are many more possibilities. The way I think about this is like we are being faced with another demotion. So as you look through the history, our importance has been going down. So at first we thought that the Earth was the center of the solar system, which was the center of the universe, of course. Then we found out that we're not the center of the solar system. The sun is the center of the solar system. Then we found that the sun is not unique, that there are 10 to the 22 of those in the universe. And the universe has no center, so we're not even there. And now we're finding that even our universe is not unique, possibly. And of course, I feel like you could have very philosophical debates, and this idea, as I said, can make people very angry and very passionate about things. But I think the only way to decide is the way we've always done in physics, through experiment. So I think there are many exciting possibilities coming very soon. So thank you.
Thank you so much. Okay, questions? Wait for the mic. I've got it. And Craig's in the back, too. There's two of us with mics.
In the black hole atom in the sky,
yeah.
If its protons are in bound to the black hole in motion. They're charged, and so they're going to emit electromagnetic radiation. Right?
Yeah. So these are not protons, right? These are not charged particles. First of all, these are neutral. They cannot be charged because if you have 10 to the 77 charged particles, I mean, this won't happen at all. So you actually have particles that only couple to us essentially through gravity. Every other interaction is very, very small. And as I said, their size is much, much bigger than a proton. So they're much, much lighter than a proton. Does that answer your question? Yeah.
I was wondering if you could expand briefly on the cantilever-based experiments. There's a number of cantilever technologies here in Santa Barbara. So.
Yes. So I didn't mention those because, I could have. I mean, I've worked on some of these things too. So, so it's another possibility. For example, in the theory, one of the big motivations behind those experiments was the theory of large extra dimensions. In fact, I have an anecdote for this from my advisor. So he was telling me, so he discovered by discussing with experimentalists that till the early 90s, we hadn't tested Newton's law at distances smaller than a centimeter. So basically, Newton's law could be much different than it is. The distance is macroscopic, that you can see with your naked eye. Okay? So you could have extra dimensions that were a centimeter in size back then. I mean, they were still allowed by all possible observations. So the theory of extra dimensions, in the theory of extra dimensions, actually, it depends on the number of extra dimensions, but the prediction is that the extra dimensions should be smaller than a few hundreds of microns. Okay, so the effect would be that as you go to shorter and shorter distances, the Newton force law, instead of going 1 over r squared, the distance squared, it would go r to the 2 plus the number of extra dimensions. Okay, so it will be dying off faster than with the distance. So people have looked for this, and this is the basis of the short distance test of gravity. Of course, there are all sorts of things. There are, for example, these particles that I talked about, the moduli, axions, can also predict deviation, new forces at short distances. So people are now, so they have tested Newton's law at 1 times gravity at around a few tens of microns right now. And there's a big effort to push for those. For example, now they don't even use cantilevers. They use optically levitated objects. They took off the clamp because if you don't have, it makes if you control something with light, it's better isolated from its environment. So it becomes much more sensitive. Thank you.
I think you said it 2 ways. You said 10 to the 22 galaxies in the universe at the end. I think earlier
galaxies,
you said
yes.
solar system.
I meant solar system, yes,
okay.
sorry.
Yeah, okay.
Yes, it's about 10 to the 11 galaxies. Sorry about that, I misspoke. Yeah.
10 to the 11.
So, galaxies, it's about 10 to the 22 solar systems.
Oh, okay. Oh.
How did I miss that?
Yeah.
You were talking about giant particles, and you were seeming like you were interchanging the word wave. Is that the same, this concept of wavicle, that they're both
yes,
and?
Yes, exactly.
They're both and.
Yes, I don't have time to go. In fact, I could spend time discussing any subtopic. Yeah. So exactly, you have it right. So every quantum mechanics tells us that you shouldn't think about particles as particles. You think about them as wave packets. So the size of the wave packet is inversely proportional to the mass of the particle. So the lighter the particle, the bigger it is. Okay? So yeah, that's why I was using it interchangeably. So in principle, mathematically, we can even describe it. We can start talking about particles. We can talk about waves. And then they would give you the same answer they should give you for what I'm talking about. But at some point, it's easier to talk about waves. It's like when people have lasers in their labs. You shine a laser if you talk about the electromagnetic mode inside the cavity. But if the intensity of the laser is very low, you start talking about individual photons. So it has to do with the number density of particles that you're talking about. So the more particles, the more wave-like it behaves. Yeah.
You talk about the extra dimensions being small.
Yes.
Or large.
Yeah.
Could you expound on what a small dimension is? I'm picturing myself living in an XY plane.
Yes.
And two-dimensional, and
yes.
somebody introduces a third dimension, Z.
Yes.
And I'm trying to picture how
So you should think about. Yes, exactly. So we don't have access to it. There's no way we feel it because photons do not propagate in those extra dimensions, but gravity does. So the way you should think about it is like, imagine you have a little circle in every point in space. There's attached a little circle. And as I said, if gravity, because it can probe these extra dimensions, as you go to shorter and shorter distances, Newton's law should change. So the way you would experience these extra dimensions is in a change of the way gravity behaves, and a change in Newton's law at short distances. But there's no way you can optically picture it other than imagine the sheet of paper with a little circle attached to each point on that piece of paper. Yeah.
Again, they work in the back.
We've talked quite a bit about waves, and Maxwell described them all. What's waving?
Sorry?
With a wave. What's waving?
So what's waving? What's doing the waving?
Yeah. We've talked about all these waves and what they are. What it is exactly that's waving?
So I think dark matter can be waving. so dark matter can be waving. Yeah. Particles around black holes can be waving. Electromagnetic forces can be waving. Several things can be waving. So the concept of waving depends on the exact. It needs to be a bit more precise than that.
So this is circular, but I would then say, what is a force? I mean, how does it do that at a distance? How does two things that are at a distance act on each other? I mean, nothing in between. I mean, what is a force? Well,
so the force is an exchange of particles, right?
I know what they do.
Yeah.
I wonder what they are.
What do you mean what they are? Define
what are they? We know what forces do. We've got all these lovely equations, but what are they? I mean, what exactly
we can describe, take the quantum mechanical theory of light, right? And we can derive from that the way photons would propagate. At the same time, from Maxwell's equation.
We know, the Maxwell.
Yes, so Yes, yeah. So we have Maxwell's equation. We can describe how photons propagate, but at the same time, from the same equation, we can derive the electrostatic force law. So they're just different regimes of the same equations. So the way you see electromagnetic waves is if you look at high frequencies, relativistic effects. So when you send a wave, right, you have an oscillation the thing that oscillates at a rate that's much bigger. The wavelength is much bigger than the distance. Okay. But if you go to things that are not changing very fast at very low frequencies, you are in the electrostatic regime. So the Maxwell's equation, this is the magic about them, they automatically can derive the force law and the wave-like behavior of the photon. They are just different regimes of the theory. So if you have two charges that are moving fast, when you're in the relativistic regimes, then you talk about retarded potentials, which is like exchanging real photons. But if you have two static charges, then you talk about the electromagnetic force, the electrostatic force. So they are just different, yeah.
I was just wondering, there are all these catastrophes in physics and all these problems. Can you hear me? Yeah. Okay.
Yeah.
And I was wondering how this unified or this attempt to unification is going to address these things. Are they going to be solved, or
it could be, as I said, it could be that the answers are not what you expect them to be. So it's not like, first of all, there are no catastrophes, right? There are unanswered questions. So I mean, we have a theory that works quite well. But it could be that there is no unique answer. There is no single unifying theory. It's just there are many possibilities, and we just happen to be one of them. So is what I said before. So if you have, depending on, so I'll say something that I said before. So initially when you had one solar system, you had to explain the dynamics that forces the orbits of the planets to be the size that they are. If you have many, you don't have to do that. It's just a historical accident. So the fact that you discover many solar systems changes the type of questions you are supposed to answer, to ask and try to address with dynamics and equations. So for example, if you have the multiverse, if you didn't have the multiverse and you had a single universe, you had to explain why the dark energy is so small. You needed a dynamical theory. You needed new dynamics, new equations. But if you have the multiverse, this is no longer a dynamical question. We do not need to find explanation for it. It just happens. It's an accident, and we have to live with it. So what it becomes, what unification? If unification is a relevant question, depends on the framework you're in. So yeah.
Hang on. Let's get the microphone to you.
Okay.
So we can hear the question.
Yeah.
So how then there's these things like subtle energies, no? So if in our universe and in our solar system we have these things that are subtle energies, and maybe they're hinting on something that is way bigger at some other universe, is that a possibility that there are these asymmetries like this?
Well, no? so usually signals from those other universes are very hard to come to us. I mean, they're basically impossible. The people have thought about the possibility that, let's say, signals from the existence of these other universes come, and it can happen during the inflationary period. If you know what the theory, if you heard of the theory of inflation is, yes. So there could be signatures of the CMB of bubbles of universes colliding very early on, at the time very close to the Big Bang. So it wouldn't be very dramatic. It cannot be some sort of very majestic, big amount of energy. It could be very, very, very subtle signatures, but people have thought about it. But it's a very, very small effect and can be easily exponentially small.
Last question,
yeah.
And we're going to break for more cookies.
Thank you. I have a question concerning gravitational waves. You mentioned the analogy with the wavelengths and the amplitude. Is there also an analogy with the light wave, with the polarization of gravitational waves?
Oh, yes.
Is there any?
Good. So that's an excellent point that you're making. So yes, gravitational waves have polarization, and in fact, people. So they are the way gravitational waves work. They make space go either like this or like this. So they make things go like this. So it's what is called a quadrupole. So there is a polarization that's a cross, and there's a polarization that's an X. So LIGO can. So if you have right now, LIGO is not very good because the two detectors are aligned. So it's not very good at looking for polarization. But with Virgo's help, which is a third gravitational wave detector in Italy, they'll be able to do better in the future. So yes, so there is polarization too with gravitational waves, and it's an important tool actually.
So only two kinds of polarization, you're saying?
Yeah.
Okay. Thanks.
Mm-hmm.
Great. Okay, let's thank Nina.
Yeah.
And for those who want more cookies, there's more in the commons room unless our physicists ate them.